Okay, thank you guys all for coming today. I know it's a weird time because of the change in schedule we had this semester, so we're doing it at a time that we don't normally have exam reviews, and I know technically you still have classes today, so I appreciate all of you taking the time to come. Just like last time, if you have questions on anything that I'm talking about, you can either shout them out at any time, or if you'd rather type them into the chat box that was working reasonably well last time. I might not get to your question right away, but I'll try to check the chat box every so often after finishing a problem, and if it comes in a little bit late, I'll just jump back to the previous topic, not a big deal. So please let me know right away if you're having trouble seeing my screen or hearing me. Sounds like we're doing okay, so I'll check the chat real quick. Seems like we're fine, and then I'll go ahead and get started with the first problem. All right, so this exam is on chapters 7 and 8 and about part of most of chapter 9. And we're going to start with problems on chapter 7. We'll go basically in order, and that's how the exam will be presented to you as well. So the first chapter deals with energy, work, heat, all those things. All right, so the first problem here is going to be to calculate the work when a sample of N2O expands from 3.75 to 8.25 liters against a constant pressure of 957 torr. So this is the only really work calculation you'll have to be able to do, which is called expansion work. It's where a gas either expands or contracts or is compressed. And the equation for this is that the work is going to be equal to the negative of the external pressure times the change in volume. Let me go back real quick and shut my camera off because last time that slowed us down a lot. So just give me a second here. All right, camera's off. Hopefully I won't have any lags this time. Okay, so this is the equation we're dealing with. It's external pressure times delta V with a minus sign out in front. And this applies specifically to expansion of a gas against a constant pressure or compression of a gas with a constant pressure. Those are the only types we're going to deal with in this course. And so in this problem, what we have to do is put in the numbers. Now, it doesn't particularly matter what units we use, but we'll notice here that all the answers are in the units of liter atmospheres, which is not a very conventional unit for work or energy, but it's the one that we're using in this problem. And so what that means is that the change in volume has to be in liters and the external pressure has to be in atmospheres. So now that we've gone through all the chapter 8 stuff, what we can know is that if we want to get the external pressure converted to atmospheres, which is what we need in this problem, we have 957 torr is the external pressure that we're given, and we're going to use the very familiar conversion factor that 1 atmosphere is 760 torr, and that's going to give us an external pressure of 1.26 atmospheres. And then remember that delta V, anytime you see the Greek capital letter delta, which looks like a triangle, that means final minus initial. So that's going to be VF minus VI, where F is final, I is initial. And so if we put those numbers in, we see that the gas expands from 3.75 to 8.25 liters. So the final volume is 8.25, and the initial is 3.75. And so our delta V is going to be 4.50 liters. All right, and then we're going to put those numbers in up here. So we have an external pressure of minus 1.26 atmospheres, and then a delta V of 4.50 liters. And by using these numbers, we have the units of atmosphere liter or liter atmospheres as is given in the answer choices, and that comes out to minus 5.67. All right, and so that's going to be the answer we would pick, which is choice B here. One thing to keep in mind is that very often we will ask you to calculate the answer in joules or some other energy unit, and the key conversion factor here is that 1 liter atmosphere is equal to 101.3 joules. And if you forget what those numbers are, if you forget this number 101.3, if you go to the periodic table that we have, which I'll get to here in a second. All right, so on the periodic table, what you'll notice is that that number is not directly given to you, although you could certainly write it on your cheat sheet that you're not allowed, that you are allowed to have, I should say. Oh, crap. It's not letting me open the periodic table. This is tragic. All right, let me just open it in here. Sorry, this is one of those work from home casualties, I suppose. All right, so here's our periodic table, and what you'll notice in the periodic table is that we give you two different values for the universal gas constant R down here. One of them is in joules in the numerator, one of them is liter atmosphere. So if you forget the conversion factor between joules and liter atmospheres, you just have to divide those two values of R. All right, so if we go back to this, basically, if you want to remember this conversion factor, you can just say that, take the two values of R, 8.314 joules per kmol divided by 0.0821 liter atmospheres per kmol. Both of those numbers are on your periodic table. We use the bottom one more often in this part of the course, but the top one comes up a little bit, especially in some of the material that we're actually skipping, but also you'll see this one a lot in chemistry too if you take that course. And this is 101.3 joules over liter atmospheres. So that's how you can remember that conversion factor if you forget it, but hopefully you don't. All right, so that was a long way of saying, here's a way of helping you remember the conversion factor. Are there any questions on that problem or that topic? I have not seen any come in. You can shout one out, or if you have a question, type it in. All right, if not, let's just keep going then so we can stay ahead a little bit. And then number two here is sort of another typical type of problem. And I'm gonna have to run away for just like 30 seconds to get a calculator because I don't, oh no, I have my phone. I can use my phone probably because I didn't actually calculate out the numbers in this one beforehand because I'm not very prepared as usual. All right, so I have my calculator here. I should be able to do this. All right. So here we want to know change in internal energy when a system absorbs 965 joules of heat and has 456 calories of work done on it. And we're looking for the answer in kilojoules and specifically. So again, for all the problems in this section, units are very important to pay attention to. So when you see the term change in internal energy, this is referring to that quantity delta E. And delta E, the definition that's going to be relevant to this problem is we're talking about heat and work, and so delta E, the change in energy, is going to be the sum of those two, Q, which is the heat, W, which is the work. And so basically those are the two forms of energy transfer that we need to consider, heat and work, and any combination of those can give you a change in energy, delta E. Now the key thing to keep in mind in problems like this is that typically Q and W are given directly to you, but you have to pay attention to the signs and to the units before we can add them together. So if you look at Q in this system, in this scenario here, we're absorbing 965 joules of heat. And so the word absorbs tells us that that heat term is positive. If heat was released, it would be negative, but here it's absorbed, so it's 965 joules. And then for the work term, has 456 calories of work done on it. Work done on the system means also that it's a positive number. Work done by the system means it's negative. So definitely review those sign conventions if you're unclear on them. But in problems like this, we're not usually going to give you directly the signs of Q and W. We're just going to give you the number, and then the context of the problem, the wording that we use is going to tell you if it's positive or negative. Absorbing heat is positive. Having work done on the system is also positive. So work here is 456 calories, but if we're going to add these two numbers together to get delta E, they need to be in the same units. You can't add two numbers together that are in different units. So then what we'll do is we'll convert this one into joules, and the conversion factor was given here, 4.184 joules in 1 calorie. And that number comes out to 1908, keeping one extra significant figure for now, joules. And so then we want to add these together, we get 965 joules for Q added to 1908 joules for W, and we get, sorry, the rest of the problems I have worked out ahead of time, so I'm not going to have these pauses in the future. So what I got was 2,873 joules, and then the delta E in kilojoules, which is the answer unit that we're looking for, is going to be 2,873 joules times 1 kilojoule over 1,000 joules. So we get 2.873 kilojoules rounded to the correct sig figs gives us 2.87. Okay, and that's going to correspond with answer choice A there. All right, so the key in these problems was to make sure we get the signs correct for delta E, and that's going to come by looking at the wording of the problem to figure out if Q is positive or negative, if W is positive or negative. Once you have the numbers, you just need to add them together. It's very simple math, but getting the signs and the units correct is usually the challenge in these. So any questions on that problem or topic? I think I had one come in. So do we need to memorize the conversion? We don't give you any, well, it varies from problem to problem. I'm assuming you're talking about the conversion we had on this last problem, which is 1 calorie is 4.184 joules. That one, we probably would give it to you sometimes, not others. It's not the same on every problem. That number, though, is also the specific heat of water, which we use all the time when we're using calorimetry, 4.184, so it's a familiar number. Also keep in mind that we do allow a one-page cheat sheet now in all the exams, which we recommend that you write on the back of the periodic table. And yes, you can still write on the back of the periodic table. So conversion factors that you're unsure about, you can always just put them on that cheat sheet if you're worried about it. But there's not too many, but these first couple of problems had a couple of the important ones, namely the atmospheres and torr conversion that we use in pressure units, and then also calories and joules, which we would sometimes use in some of these other problems. And then we have a question that came in about exam readiness report. So basically, we're not going to do another exam readiness report. We're going to keep the same settings for you guys that were on the previous exam. If something in your life changed between the previous exam and now, you can let me know individually, but we're not going to have a separate exam readiness report for this exam. All right, any other questions for now? All right, so let's move on then to the next question here. So this question is more of a conceptual question dealing with an exothermic reaction. So the reaction between HCl and NaOH is exothermic. Which of the following statements about this process is correct? We're looking for the true statement here. So let's just sort of evaluate these one by one. So choice A, delta H is positive. That one is not going to be correct because exothermic, what that is defined as, is a negative delta H. All right, so exothermic means negative change in enthalpy. If we look at B here, for this one, the enthalpy of the products are greater than the enthalpy of the reactants. So to think about how this one works, basically remember that delta always means final minus initial. And in the context of a chemical equation, that means products minus reactants. Products is the final state that you would have in a chemical reaction. Reactants would be the initial state. So if we're talking about delta H, it's going to be the enthalpy H of the products minus the enthalpy of the reactants. Okay? Now we don't usually deal in terms of absolute enthalpies, but this is what it would be defined as if we were thinking about it in those terms. And this number, as we said, because it's exothermic, is less than 0. And then so if we rearrange this inequality, this would tell us that for an exothermic reaction, the enthalpy of the products is less than the enthalpy of the reactants. All right. Another way of thinking about this is if delta H is negative, that means the enthalpy is decreasing during the reaction, and that means the products have lower enthalpy than the reactants. So this one says that the enthalpy is greater than the reactants. That's again opposite of what is true. So both of those first two are false. If we go to choice C, the temperature of the surroundings increases. And so when we're dealing with products that involve processes that involve enthalpy changes, in particular chemical reactions that we're talking about here, whenever you have an exothermic process, remember that delta H is also it's defined as the heat of the reaction at constant pressure. So if we carry out the reaction at constant pressure, the heat that we measure is equal to delta H. And so if we have an exothermic reaction, that means heat is negative, meaning heat is released. And if heat is released to the surroundings are going to absorb that heat and their temperature is going to increase. So in an exothermic reaction, the temperature of the surroundings increases. An easy way to remember this sort of practically is if you think about setting something on fire. You know, one of my favorite pastimes from when I was a kid, always in a safe way, of course. When you set something on fire, you're burning it. That's an exothermic reaction that, of course, releases a lot of heat and then increases the temperature of whatever's around it. So exothermic reactions always increase the temperature of the surroundings. So this one appears to be true. Let's evaluate the other two answer choices just to see why they should be false, and if they are. The bonds in the products are weaker than the bonds in the reactants. This sort of harkens back to some things we learned a while back, I think in chapter 3 or something. Yeah, I think chapter 3 of this course. And remember that the enthalpy change can be approximated as the sum of the bond energy of the reactants minus products. This was sort of the first way we learned how to calculate this. We called it delta E at the time, but it really was delta H. We just hadn't introduced delta H yet, so we didn't want to confuse you with that. But remember that we can take and approximate delta H by taking bond energies on the reactant side and subtracting the bond energies on the product side. And again, because this is negative, less than 0 for an exothermic process, if we rearrange this, this means that the sum of the bond energies on the product side are going to be greater than the bond energies on the reactant side. So in an exothermic reaction, the bonds on the product side are, sorry, I ran out of room as I always do. But in an exothermic reaction, the bonds on the products are stronger than the bonds on the reactants. And so this one would be false because, again, it's the opposite of what it should be. So in an exothermic process, basically you're forming chemical bonds which have a lot of potential energy, and those chemical bonds are stronger, and you release that excess energy as heat, and that's why it's exothermic. And then finally, for choice E, the reaction absorbs heat from the surroundings. As we already said in one of the earlier choices we were analyzing, exothermic, where you have a negative delta H, means that heat is released. Right? So that's a key definition also of exothermic, meaning that the heat term is negative, heat is released to the surroundings, and so again, this one is the opposite of what it should be. All right, so choice C was the only correct one. This test doesn't have a ton of conceptual questions, but this would be one that could be on there, dealing with sort of some concepts related to enthalpy changes, heat, and so on. So do we have another question come in? I think that was just a previous one. Any questions on this topic or this problem that I just went through? All right, I won't dwell too long, but if you have something that you're still working on, please let me know and I'll get to it a little bit later. All right, so number 4 here is a problem dealing with what's called a thermochemical equation. So a thermochemical equation is a chemical equation along with the associated delta H. And what we want to do here is we want to know what is the enthalpy change when 12.5 liters of C2H6 measured at 25 Celsius and 780 torr is burned in air. So basically we're taking 12.5 liters of ethane, as it's called, C2H6, one of the components of natural gas, but not the major component. We're burning it in air and we're getting these products. We want to know what's the enthalpy change. So in problems like this, you almost treat them a lot like a stoichiometry problem, and this one even takes it a step further because it actually combines concepts from both chapter 7 and 8. Now, I don't think there's any problems on the exam that do that exact same thing, but this is a good one to go over in a review session because it gives us a little bit of practice on sort of both of those aspects that we're going to be responsible for. So in a problem like this, what this thermochemical equation tells us here is that if we burn 2 moles of C2H6, we're going to release 2,855 kilojoules of heat, or the delta H will be minus 2,855. So that's what that thermochemical equation tells us. We want to know what is delta H when we burn this much ethane, 12.5 liters, at a temperature of 25 Celsius and a pressure of 780 torr. So what you need to do in these types of problems is you need to first figure out how much of the reactant do you have, in this case the C2H6, how many moles of it do you have. So what we're going to do for that is, because that is a gas phase reactant, we're going to use the ideal gas equation, PV equals nRT, to figure out how many moles of that we're actually burning. And then once we know how many moles of that we're burning, we can relate that to the thermochemical equation given above. So what we have to do first is convert the pressure to atmospheres, because if we're going to use the ideal gas equation, that's going to be the conventional unit we use. So again, same conversion we did in the first problem, 780 torr, and then 1 atmosphere is equivalent to 760. So we get about 1.03 atmospheres, not too different than 1 atmosphere. And then if we want to find the moles of C2H6, we're going to rearrange the ideal gas equation and plug in all the numbers. So the moles of ethane we have is going to be PV over RT. So the pressure we just found was 1.03 atmospheres. The volume is given as 12.5 liters. And then RT in the denominator. R is the universal gas constant. It's on your periodic table, but you should probably know it by now if you've done enough of these problems. 0.0821 liter atmospheres per k mole. And then the temperature needs to be in Kelvin for any ideal gas calculation. 25 Celsius is going to be 298 Kelvin. Add 273 to that. And so what we get for the moles of C2H6 is 0.526. And then once we have moles of the limiting reactant, we can use that to figure out what the delta H would be. And so we're going to treat this now sort of like a stoichiometry calculation. The delta H is going to be, we have 0.526 moles of our reactant. And the chemical equation that we're given tells us that delta H is going to be minus 2,855 kilojoules. And that's going to be the delta H when we burn 2 moles of C2H6, because C2H6 has a coefficient of 2 in front of it. So we're going to put 2 moles here in the denominator. So moles cancels out, and that's going to give us then the number of kilojoules that are released when we burn this much C2H6, and that comes out to minus 750.9 kilojoules. And this is a numerical question, so we would enter the answer just as minus 750.9. All right, so that's going to be how we handle these thermochemical equation problems, where if we want to find delta H for a process, we basically treat it like stoichiometry. We find moles of whatever reactant or product they're asking us about, and we relate that to the delta H that's given to us, keeping in mind that this delta H is going to correspond to the coefficients that are given. 2 moles of C2H6, 7 moles of O2, forming 4 moles of CO2 and 6 moles of water. So that's kind of how we would approach those. All right, any questions on this one or the topic? All right, I think that last message that came in was just the previous one I saw. All right, so if we're good on that, I will move on then. I'll try to keep it going to number 5. All right, so number 5 deals with one of the 2 major types of calorimetry problems we can have. So remember, a calorimeter is a device used to measure heat, and then we can use that in a few different applications, either measuring a physical property like a specific heat capacity that we're doing here, or as we'll see in the next problem, measuring something about a chemical reaction. Usually it's delta H. So here we're measuring, is related to just heat transfer. So we have 5 grams of copper. Copper slug is just a chunk of copper. With this given heat capacity, 0.385 joules per gram degree Celsius, it's heated to a temperature of 100 degrees Celsius. We place it into a cup of 10 milliliters of water, which is initially at 23 degrees Celsius. We want to know what is the final temperature in degrees Celsius, assuming no heat is lost. Enter your answer in 2 decimal places and no units. All right, so what we're doing in these problems is, in this case, we're just doing a physical process, heat transfer. We're not doing a chemical reaction. The copper's not reacting with the water. It's just that we're putting 2 things together that have different initial temperatures, and whenever you do that, there's going to be heat transfer between them, and that heat transfer is going to occur until the temperatures of the 2 objects are equal. So here what we basically have is the heat for the copper is going to be equal and opposite to the heat term for water. So the 2 objects that we're putting together are copper, which is initially at higher temperature, and then water, which is initially at the lower temperature. We put them together, there's going to be heat transfer between them, and the quantity of that heat calculated for both systems is going to be equal in magnitude but opposite in sign. So then we can rearrange this, because for both things, copper and water, the heat can be given as mc delta T. So the mass of copper times its heat capacity times its delta T is equal to the negative of the mass of water times the heat capacity of water times its delta T. And it doesn't matter which side of the equation you put the minus sign on. That's sort of arbitrary and up to you. The other thing that's important to keep in mind is that this delta T term, so the masses and the heat capacities are all known already. Water is not given, but you should already know it, or you can put it on your cheat sheet if you're worried about forgetting it. But remember, for each of them, the delta T is going to be the final temperature minus the initial temperature. Delta always means final minus initial. And so this is what we're solving for, is the final temperature, which will be the same for both. Basically, the heat transfer is going to occur until they reach the same final temperature. They are going to have different initial temperatures that we're going to have to account for. Okay, so then when we put the numbers into this equation up here, the mass of copper is given as 5.00 grams. The heat capacity of copper was given as 0.385 joules per gram degree Celsius. And then delta T for copper, final minus initial, TF is what we're solving for. The initial temperature for copper was 100 degrees Celsius. For these problems, it doesn't matter if you use Celsius or Kelvin, as long as you're doing a delta T, because the difference in temperature between Celsius temperatures and the corresponding Kelvin temperatures will be identical. But only when you're using delta T do you not necessarily have to convert to Kelvin. It wouldn't be wrong to, but you don't have to take that step if you don't want to. And then if we go for the water, there's a negative sign out front. We have 10 milliliters of water. Recall that the density of water is 1. That's the only density you have to memorize, is water, which is 1. And 10 milliliters means that we have also 10 grams if the density is 1. So we have 10 grams of water. The heat capacity of water, this is the only heat capacity you have to know that we won't necessarily give you, 4.184 joules per gram degree Celsius. And again, that's also the conversion factor between calories and joules. And then the delta T for water is going to be that same TF that we're solving for. The initial temperature for water was 23.0 degrees Celsius. Okay, so this is the math, or this is the setup anyway. The algebra is not too bad, but it's also not trivial. I'm not going to go through all the steps, so I'm going to put my magic algebra arrow in here. But I encourage you to work through it yourself to make sure you can get this. And what I ended up with was a final temperature of 26.39. We asked for 2 decimal places, so that's how we'll report it, degrees Celsius. So we're looking for this number here. That's what we would put into Blackboard. All right, so there's a few different variations on problems like this. This one asks us to solve for final temperature. Another common situation is that we give you the final temperature and you have to solve for an unknown heat capacity, usually of the substance that's not water, of course. And there's a few different variations where basically any of these terms in the equation up here could potentially be your unknown, but it's really just the same mathematical setup every time, just solving for the correct unknown that we're asking you for. Okay, any quick questions on that? All right, and then moving on to number 6, this is sort of the other application of calorimetry. So the other application of calorimetry is basically to measure the delta H for a chemical reaction. So what we're looking for here is, so we typically do these in bomb calorimeters, but there's not really a fundamental difference between a bomb calorimeter and a regular calorimeter, at least that we have to concern ourselves with. So we have a bomb calorimeter with a heat capacity of 9.25 kilojoules per Kelvin, filled with 1 liter of water. We take a 5-gram sample of acetic acid and we burn it in the calorimeter. So most often we're doing combustion reactions in these, but not necessarily the case. And that raises the temperature by 5.40 degrees Celsius. We're going to use this information to determine the enthalpy change for the combustion of acetic acid. So for 1 mole of acetic acid is given below. Okay, so there's a lot of stuff going on here in these types of problems, but what we're eventually going to want to get to is an enthalpy change for this combustion reaction down here, for the burning of 1 mole of acetic acid. All right, and so what we're basically doing in these problems is what we're going to first do is we're going to calculate the heat for the calorimeter. All right, so that's going to be really the first step in these types of calorimetry problems that deal with chemical reactions in a calorimeter, is to calculate Q for the calorimeter. And the way we do this is there's going to be 2 terms we have to consider. So the calorimeter typically has water in it to absorb a lot of the heat. So we're going to use MC delta T for water to figure out how much heat is absorbed by the calorimeter. And then we're going to add to that the heat that's absorbed by the calorimeter itself. So the container that the water is in, whatever other materials are sort of around, surrounding the calorimeter, the casing material as it is. And that's going to be just given as the heat capacity of the calorimeter times delta T. That's going to be given to you as just a total heat capacity, not a specific heat capacity. So there's no mass term associated with that. So these are the problems that we have. These are the two terms that we have. And as I've pointed out in both the lecture and in some of the review videos that I've done since then, which of these two terms we use is going to depend on the information in the problem. So sometimes we make the assumption that all of the heat is absorbed by the water, and the heat absorbed by the calorimeter is negligible, and so we just eliminate the second term. Or sometimes we just group everything together, water plus calorimeter, into one big term. So which of those two terms you use, sometimes both of them, sometimes only one of them, depends on the information in the problem. Now in this problem here, we're telling you how much water is in the calorimeter, 1 liter, which we can easily convert to the mass of water. So we have the information we need for that term. And we're also telling you even earlier that the heat capacity of the calorimeter by itself is 9.25 kilojoules per Kelvin, so we have that number as well. Okay, so we have both terms, so we're going to have to count for both of them when calculating Q for the calorimeter, calculating the heat. So let's start putting in the numbers now that we have. And there's some conversions we have to do, but I'm going to mostly gloss over those. But the mass of water goes in first for the MC delta T. We have 1 liter of water, that's 1,000 milliliters, which is equivalent to 1,000 grams. So typically for MC delta T, we want to use grams as our mass unit. The heat capacity of water, which we actually gave you here, is the same number that we used last time, 4.184 joules per gram Kelvin or gram degree Celsius, is in terms of delta T, so either of those is the same. And then the change in temperature, we're telling you the temperature increases by 5.40 degrees Celsius. That means delta T is positive 5.40. We didn't give you individual temperatures here, we just told you the change. And the other thing we have to be careful with is the units. So we want enthalpy change in kilojoules per mole. This term here would be in joules. So we could calculate it out individually, but I'm going to go ahead and just in one step convert it to kilojoules by dividing by 1,000. Okay, so that will give us the first term in kilojoules, which will give us closer to our answer. And then for the second term, the heat capacity of the calorimeter times delta T, that is given to us up here as 9.25 kilojoules per Kelvin. So we don't have to do anything with that number to convert it. It's just going to be 9.25 kilojoules per Kelvin or kilojoules per degree Celsius, whatever your preference is for that for delta T. And the delta T is 5.40, which can also be written as 5.40 Kelvin. So for delta T's, Kelvin and Celsius is interchangeable, as we said. So these are the two terms. This one's already in kilojoules, so we don't have to convert it. This one we did the extra step to convert it to kilojoules so that we can now add them together. We can make sure they're in the same units, either joules or kilojoules, before we add them. So that comes out to 72.5 kilojoules. Now that, unfortunately, is not our final answer. We have one more step to do. Technically 2 more steps, but one of them is trivial. So this is the heat for the calorimeter. What we're looking for is the heat of reaction. So the heat for the reaction that we're carrying out in the calorimeter is just the negative of that. So it's going to be negative 72.5 kilojoules. That's still not our final answer because this is the heat, or the delta H, associated with burning 5 grams of acetic acid. What we want is we want to find out the heat that's associated with burning 1 mole of acetic acid, because that's the chemical equation we have down here with the coefficient of 1 in front of acetic acid. So then what we have to do is to find delta H, we have to take the heat of reaction and divide it by the moles of substance that we were burning, in this case the acetic acid. All right, and so to get moles of acetic acid, we have 5 grams and then 1 mole of acetic acid. I don't know if I gave that to you here or not. I did. So the molecular weight is 60.02. So we're going to use that to convert grams to moles. So it's 0.0833 moles. So that's what we're going to divide. We're going to take the heat of reaction minus 72.5 kilojoules, which is the amount of heat for burning 5 grams. We're going to divide that by the corresponding amount in moles to figure out how many kilojoules per mole that we're going to have. And that's going to be minus 870.3. This was another numerical question, one in 1 decimal place, so we're going to leave it as that. All right, so this tells us that when we burn 1 mole of acetic acid, delta H is minus 870.3 kilojoules. One thing to point out about this problem, actually two things I want to point out. First of all, the most common mistake that people make, or one of the most common mistakes they make, is basically to use this mass incorrectly. So this mass does not go into the MC delta T equation. The MC delta T is the mass of water in the calorimeter that's absorbing the heat. This is the mass of the reactant that's burned. We don't use that until the end. Down here, we're figuring out how many moles of the reactant was present. We're assuming again that all the heat is absorbed by the water and the calorimeter, so the only mass term we need to calculate that is the mass of water, not the mass of the substance we're reacting. The other thing to point out is that number 6 here, this last step of number 6, where we divided the heat by the number of moles of substance to get delta H per mole, I guess I could write that as per mole if you want to be more specific. To get this number here, this was actually the reverse of what we did in number 4. So if you think back to number 4, we basically took moles of substance and converted to delta H by using the thermochemical equation. In number 6, we did the opposite. We found the heat of reaction, this number here, and divided by moles of substance to get the delta H for that given chemical equation. So we worked sort of in both directions on these problems. They are related to each other. Hopefully that's more clear now how those are sort of related. All right, so any questions on this topic dealing with calorimetry? There are only 2 problems on the same topic. Haven't seen anything come in. All right, so here's the question was, how do we get 1,000 grams of water, milliliters to grams? That is correct. I went through that fast, but we're told in the problem that we have 1 liter of water. 1 liter is equivalent to 1,000 milliliters. The density of water is 1, so 1,000 milliliters is equal to 1,000 grams. So I did that kind of quickly, but basically it was 1.00 liters of water, 1,000 milliliters in 1 liter, and then the density is 1, so it's 1 gram per milliliter. So that's how we would get 1,000 grams. That's exactly right. Okay. Any other questions? All right, I'll move on then to number 7. All right, number 7 is a typical problem type. You're likely to see one of these on your exams, which is called Hess's law. We're basically using 2 or more given thermochemical equations to calculate an unknown delta H. These problems are fun if you like puzzles, so they're kind of like a puzzle in some sense. If you don't like puzzles, then I apologize. This won't be the most fun problem type for you, but they're not too bad, and there's sort of a method we can follow to getting these that's going to work every time. We just have to make sure we're detail oriented and following things closely. All right, so we're looking for the delta H of formation of B2H6, and we have all these given information down here. So the first thing we need to do is figure out what is the chemical equation that's associated with delta H of formation for that substance. In a lot of these problems, we actually give you the chemical equation, and then you're going to use the 3 given equations to produce that. Here we have to figure out what is the chemical equation associated with delta H of formation. So this is a good review of what a formation equation is. So remember, in a formation equation, we're forming that substance, that compound, as a product. We're forming 1 mole of it. So this will be the product of our formation equation, and then the reactants are going to be the elements in their standard state. So the standard state of boron is just B. Remember, the standard state for hydrogen is actually H2 gas. Boron solid, H2 gas. So those are the 2 reactants. Then we just have to put coefficients on the left side of the equation only to make this balanced. So we put a 2 there and a 3 there. So this is the chemical equation we're trying to find. The delta H for this is going to be the delta H of formation of B2H6, because this is the formation equation. And that's what we're trying to figure out here. So what we have to basically do then is figure out how to combine these 3 given equations, or maybe not all 3 of them, but at least 2 of them, to get this equation here. So the way we want to do this is we want to look for the reactants and products in the unknown equation and see where they appear up here. And ideally we want to find reactants and products that only appear once in the given equations. So if we see boron, we have 2 borons as a reactant in the unknown equation, and this first one here, which I'll number 1, 2, and 3 to keep them straight from each other, this first equation is the only one that has a boron in it. We have 2 borons in our unknown equation that we're trying to get to. We have 4 borons up here, so what we're going to have to do is we're going to have to take all the coefficients in the first equation and multiply them by 1/2. Let me write that as 1/2 times equation 1. So that's the first thing we're going to do is we're going to take this first given equation, we're going to multiply all the coefficients by 1/2. So I'm going to leave out the states of matter just to save some time. We get 2b plus 3/2 O2 goes to B2O3. So that's our first modified equation, and because we multiplied all the coefficients by 1/2, the delta H gets modified by the same factor, 1/2. So we're going to take this delta H and multiply it by 1/2, we get something like minus 1254.6 kilojoules. So that's the modified delta H. So now we have 2 borons on the reactant side. We also want to have 3 H2s on the reactant side. H2 only shows up here in the second given equation. This has a coefficient of 2. We want it to be a coefficient of 3, so what we're going to do is we're going to take the second equation and we're going to multiply it by 3/2, or 1.5. So if we take 3/2 times equation 2, that's going to give us the correct coefficient for hydrogen, 3, which is what we want. All right, so we're going to multiply all the coefficients by 3/2. We have to do everything. We have to do the same thing to every coefficient to keep it balanced. So 3H2 plus 3/2 O2 goes to 3 waters. And the delta H for this modified equation 2 is going to be, again, the same factor we multiply the coefficients by is going to be multiplied by delta H. So this number up here, minus 571.7 times 3/2 is minus 857.6. And then finally, the last thing is we have to have B2H6 as a product. B2H6 only appears in the third given equation, but it's on the reactant side. So to get B2H6 on the product side, we have to flip this whole third equation, which basically means inverting reactants and products. Everything on being switched to the opposite side of the arrow. So we're going to take the inverse, or the negative, of equation 3. So that's going to put B2O3 and 3 waters on the reactant side, and then these products are going to be flipped over to the, these reactants are going to be flipped over to the product side and give us B2H6 and 3O2. And then whenever you flip a chemical equation, the delta H just changes its sign. We didn't do anything to the coefficients, so we don't have to multiply it by any other factor, but anytime you flip the equation, you flip the sign of delta H. So it's going to be negative of that third delta H, or positive 2,147.5 kilojoules. All right, so those are the 3 modified equations. Now you don't necessarily have to add them all together. If you trusted that you did these previous steps correctly, you can now just add the numbers together and you'll get the answer. That said, it's good to check yourself and make sure that the 3 given equations that you have, that they all add up properly to give you your unknown equation, the delta H, or formation equation for B2H6. So let's check that that works out. So basically when you add together chemical equations, everything on the left side of the arrow gets added together and is now on the left side of the arrow of the combined equation. Everything on the right side also gets added together, just like we're adding mathematical equations, and then anything that's on both sides of the arrow cancels out. So we have 2b that carries through, that doesn't cancel out with anything. 3H2, 3/2 O2 plus 3/2 O2, total of 3 O2s on the reactant side, as well as 3 O2s on the product side. So O2 cancels out. There's 3 O2s on both sides of the arrow once we add everything together. We have 3 H2 that doesn't cancel with anything else. And then here we have B2O3. B2O3 appears here as a reactant, but it cancels out with this B2O3 that's on the product side, so we don't have any B2O3. And then our 3 waters, 3H2O here on the reactant side, 3H2O here on the product side, they cancel out. And then all that's left on the product side is B2H6. So that verifies that these 3 modified equations add together correctly to give us 2 boron plus 3H2 going to B2H6. And then the delta H of this, which is the delta H of formation for B2H6, is going to be just these three numbers added together. Minus 12 minus 857.6 and then plus 2147.5, and so we get positive 35.3 kilojoules. Sorry, I left out some units. Kilojoules, those are all kilojoules. So we're just adding these three numbers together. And so we get 35.3, which matches up with answer choice B up here. I apologize if there's some background noise. Someone they're mowing the grass in the walking trail outside of my house, so it's a little bit loud out there. Hopefully that'll end soon. Do we have any questions on that problem though? Or that topic in general? So that's Hess's law for us. Again, it's a lot like putting a puzzle together of just trying to figure out how to arrange the three given equations to get an unknown delta H. So if there's no other questions on that, I will move on to the next one. And this problem here is somewhat related, but the difference here is that here we're looking again for a delta enthalpy of formation, but in this problem we're also just giving you all delta H of formation values, as well as a delta H for a reaction down here. So in problems like this, where all of the given enthalpies are formation enthalpies, delta H formation, we're also solving for delta H formation, we should recognize that there's sort of a shortcut to this. So for this equation here, delta H, which is sometimes called delta H of reaction, Rxn, is equal to the sum of the delta H's of formation of the products minus reactants. So this is another way for us to calculate delta H. If we have all of the delta H of formation values for the products and the reactants, we can take the sum of the delta H of formation for the products and subtract them from the sum of the delta H's of formation on the reactant side. So products minus reactants in this case. The M and N values that we have here are basically the coefficients. We have to account for the coefficients because each enthalpy of formation is per 1 mole of substance. If we have a coefficient that's not 1, we have to multiply the delta H by that coefficient. And so in this problem here, that's going to be the shortcut we want to use. We could write out all of the chemical equations, and we could then figure out how to combine them like we did in the last one, but that's a lot more time consuming, a lot more work than is necessary here. In this case, because everything we're dealing with is a formation enthalpy for the reactants and products, we can just use this mathematical relationship. And in this problem here, then, the unknown is going to be the delta H of formation for NH3, which is one of our reactants. So if we start putting numbers in, the delta H is given to us for the reaction is minus 1134.4 kilojoules. And if you'll forgive me, I'll put units in just so you guys don't get mad at me, even though you never do. And that's going to be equal to, again, the sum of the delta H's of formation for products minus reactants. So on the product side, we have 4 NO2s, and the delta H of formation for NO2 is given here as 33.2 kilojoules. And then on the product side, we also have 6 water in the gas phase, so we have 6 in the gas phase. Enthalpy of formation for water is minus 241.8. So that's the product side, and then on the reactant side we have 4 ammonias, and that's going to be our unknown. 4 times the delta H of formation for ammonia, NH3, that's what we're solving for. And then we also have 7 O2 on the reactant side. What we have to remember about problems like this is that if you have an element in the problem, an element in its standard state, the delta H of formation is always 0. So for O2 gas, which is the standard state for oxygen, the delta H of formation is 0, and so when we add that on the reactant side, it's just going to be 7 times 0. So we don't need a delta H formation for oxygen, it's going to be 0 by definition. So that just goes away. Alright, and so all that leaves us with is this unknown here, delta H of formation for NH3. We just do a little bit of algebra to solve for it, and what we end up with is minus 45.9 kilojoules. All right, so this is really, there's only really two major variations in problems like this. Here we were solving for delta H of formation as one of our unknowns. In other types of problems, we'll give you all the delta H's of formation and you have to calculate the delta H, which would not be given to you in that case. So just the same relationship in both cases, just different unknowns you have to solve for. And anytime you're dealing exclusively with delta H of formation, and only when you're dealing with delta H of formation, you can use this relationship here. The delta H for the reaction is the sum of the formation enthalpies of the products minus reactants, and that will be a nice fast way to do those problems without having to write out a million chemical equations. So any questions on that topic? Making sure I'm not missing any messages because Teams just told me that I was in do not disturb mode, which means that I might not get all the messages. Hopefully I'm not missing, as long as you send the message within this meeting, I should get it. So if you're trying to message me and I don't respond, then just shout it out because I may not be seeing it. But I think I'm getting all the messages from you guys. So if there's no further questions on that, let's move on to this one. Now this problem is a little bit involved. Not very likely you'll see one exactly like this on the exam, although there are some in the question bank that are related. And we have basically one of the question sets on the exam deals with things related to energy and fuels, basically, you know, sort of the important practical applications of enthalpy and heat and work and all that stuff. So there's one section in the notes about that sort of summarizes, I think, what's the important stuff to know. There's a section in your book if you want to read it in more detail. And most of those questions are just conceptual or knowledge-based questions. There is one type, though, that you might get that's a lot like this one, which talks about how burning a fuel gets converted into electricity. And so this problem here, we have methanol, which is C4H4O is the chemical formula, is being considered as a possible fuel source for the future. And the combustion enthalpy of methanol is minus 715 kilojoules per mole, has a density of 0.792 grams per milliliter. So the question that we're finally asking is, if 1 liter of methanol is burned to produce electricity, how long would it power a 60-watt light bulb, assuming 100% efficiency? So again, this is sort of a conversion of chemical energy from burning a fuel into electricity and then deciding how much electricity that produces. So this ends up just being a very long conversion, sort of dimensional analysis type problem. So the first step is going to be very similar to what we did on one of the earlier problems, which is we have an amount of a substance, we have an enthalpy, in this case a combustion enthalpy per mole, and we're going to first start out by figuring out how much enthalpy change do we have, in other words, how much energy is released when that substance burned. So we'll do this all as one long string of conversions. We're looking for how much time this is going to burn a light bulb, but we're going to get there first by figuring out how much energy is released when this substance burns. So we have 1 liter of methanol, C4H4O. And the first thing is going to be to convert it to moles because the combustion enthalpy is in kilojoules per mole as it normally is. So how do we convert liters into moles? For a liquid, that's going to be sort of a 3-step process just to get to moles. So once we have the volume, we can convert it into mass using the density, but that's going to require us to go to milliliters first. Because the density is grams per milliliter, so we're going to convert to milliliters first. So that's milliliters of methanol, and then we have the density, which is grams per milliliter, that allows us to figure out how many grams of that substance we have. So these first few conversions should be fairly familiar to us. So 0.792 grams of C4H4O in 1 milliliter. That's just using the density as a conversion factor to go from volume into grams. Once we have grams of the substance, we can convert to moles. The molar mass is 32.0. So 1 mole of C4H4O has a mass of 32.0 grams. So once we have moles of substance, now this next step is going to be identical to what we did in, I think it was problem number 4 a little bit earlier. We're going to use the combustion enthalpy to figure out what is the delta H, or what is the energy that's released when this many moles of methanol burns. And so it's going to be 715 kilojoules released per mole. We don't necessarily have to put that as a negative number because we're looking for how much energy is released, so it's just a positive term, and our final answer should be positive anyway because it's amount of time. So that's how many kilojoules we produce. And then from there, the rest of this is going to be a little bit less familiar, but what we're going to do is we're going to recognize the hint that's given to us. When we have a 60 watt light bulb, capital W, if you've taken physics, this should be familiar, but if not, we gave you the clue here, which is that 1 watt is equal to 1 joule per second. So basically a watt is how fast you're burning the energy, and we can also use then this 60 watts as a conversion factor to relate how much energy we're consuming to how much time it's going to take to consume that energy. So the first thing to do is, because a watt is in terms of joules, we're going to convert this to joules first, 1,000 joules in 1 kilojoule. And then we can use 60 watts as a conversion factor. So 60 watts is the same as saying we burn 60 joules in 1 second. So if we write it in this way, the joules cancels out, and we're told that gives us how many seconds we have. Now the annoying part about this problem is that our answer choices are in 3 different units. So if we just work this out now, we get 2.95 times 10 to the 5th seconds. That does not match any of the 4 answer choices. If we divide that by 60, we get 4.9 times 10 to the 3rd minutes. We're just converting seconds to minutes. That doesn't match any of the answer choices. And then finally, if we divide this by 60 again, that'll give us the hours, which is 81.9 hours. So the correct answer for this would be choice D, which is 81.9 hours. Again, set up in an annoying way because the answer choice said 3 units, but once we get seconds, we should be familiar how to convert seconds to minutes, minutes to hours, just dividing by 60 each time. Okay, so again, that problem is not one that you're necessarily likely to see, but it probably is the most involved problem in this problem set here, number 9, which deals with fuels and energy and things related to that. All right, but if you did dimensional analysis, you could hopefully figure out how to piece this together, even if some of the concepts, in particular the last one here with wattage, was unfamiliar. Okay, so do we have any questions on that problem or any of the related topics? All right, number 10 now, we're finally transitioning into the ideal gas part of the test. So we're getting into chapter 8 material, if you're keeping track that way. And so there's going to be a lot of questions of this type. And again, most of these will involve numerical calculations, just like the previous ones. So in this problem, we have a balloon filled with an ideal gas, which has a volume of 253 milliliters at 24 degrees Celsius. What is the volume if the temperature is increased to 86 degrees Celsius? So there's a lot of different relationships between the properties of an ideal gas: pressure, volume, temperature, number of moles, all different combinations of those. You don't necessarily have to memorize individual equations because everything can be derived from the single ideal gas equation, PV equals nRT. So in this problem, we're relating volume and temperature. And so, and those are going to be the 2 units that are changing. Everything else we're assuming is constant. So what we're going to do is the 2 variables that are changing, volume and temperature, we're going to move those over to one side, and then we're going to move everything that's constant over to the other side. Okay? So volume over temperature, rearranging, is equal to nR over P. So we're just doing a little bit of algebra to move volume and temperature over to the same side of the equal sign. Now you might ask, how do I know all these are constant? Well, R is always a constant, is a universal gas constant, of course. Number of moles is constant because it's a balloon, so assuming the balloon's not leaking, you're not going to have any change in the number of moles of gas that are inside of that balloon. And then pressure, we don't specifically tell you that it's constant, but we don't tell you anything about pressure. So if there's one of the variables that we don't tell you anything about, you have really no choice but to assume that it's constant. So this is going to be equal to a constant. And what that means then is that the initial ratio V1 over T1 is going to be equal to the final ratio V2 over T2. You could have also inverted both sides. It doesn't matter whether you put volume or temperature on the top or bottom, but you're going to get some equation that looks like this that we can use. And so what we're solving for is the volume at the higher temperature, so we'll call that V2, final volume, and that's going to be, if we do some algebra here, V1 times T2 over T1. For problems like this, if we're not using R, the universal gas constant, we can have volume in whatever units we want. So in this case, we'll just keep it as milliliters since that's what all the answer choices are. But the one thing that you must do in all of these problems is you must use temperatures in absolute units of Kelvin, okay? So T1, which is the initial temperature, is 24 degrees Celsius. We have to convert this to Kelvin for this to work. So in ideal gas problems, you absolutely have to use Kelvin temperature units. That's not negotiable. All right, so the initial temperature is 24 Celsius. To convert it to Kelvin is 297. And the second temperature, T2, was 86 degrees Celsius. And that's going to convert to 359 Kelvin. Okay, so those are the two temperatures we're going to use. T2 in the top, which is 359. And then T1 in the bottom, which is 297. And that works out to 306 milliliters, okay? So we do expect the volume to increase because we're raising the temperature, and that's going to cause the gas to basically move faster and push harder on the walls of the container, and then the correct answer then would be C, 306 milliliters. All right, so any questions on that one? All right, you guys are quiet today, so hopefully you're following along with everything. If there's any questions that I don't cover, please you can type them in the box anytime or interrupt me at any time, and then we can also talk afterwards if there's something that you're still not following. All right, the next question here is related. It's also going to deal with the ideal gas equation. So we have a steel tank with a fixed volume, so that means volume is constant. And that's going to be filled with 126 grams of nitrogen at 298 Kelvin, giving a pressure reading of 235 kilopascals. What will the new pressure in kilopascals be if 96 grams of N2 is added and the temperature cools to 273 Kelvin? So if we start with PV equals nRT, in this problem, of course, R is always a constant, volume we said is a constant, but pressure, number of moles, and temperature are all changing. So again, we're adding gas to the tanks. That means we have more moles at the end. And we're telling you that the temperature goes from 298 to 273. And then we're trying to figure out how that affects the pressure. So that, of course, is going to be changing. So when we rearrange in this case, we get pressure, number of moles, and temperature on one side, and then R and volume on the other side. You could have also rearranged this the other way and put NT over P equals V over R. It'll get the same answer either way. And so when we then write this out in terms of the initial and final states, P1 over N1 T1 equals P2 over N2 T2. Okay, so this is sort of a non-standard gas equation. It's not one of our typical ones that we deal with, but we can always derive it from the ideal gas equation. And so then what we're solving for here is the final pressure P2. And so P2 is going to be P1 N2 T2 over N1 T1. And we can then put those values in. So a lot of these are going to be given to us directly in the problem. So we have P1 is the initial pressure, which is 235 kilopascals. And again, for problems like this where R drops out, we can use whatever units of pressure and volume we want. But here's where you have to be a little bit careful is for N2 and N1, we're not given those directly, we're given masses. And so if we calculate N1, which is the initial amount that we have, that's 126 grams. So N1 is 126 grams of N2. The molar mass of N2, which I didn't give you here, is 28. And that comes out to 4.50 moles. So that's N1. Now N2 though, here's you have to be careful. N2 is not just the amount that we're adding. It's not just 96 grams converted to moles. N2 is the total number of moles of nitrogen we have at the end. So if we're adding 96 grams, that means N2 is going to be the amount that we initially started with, 4.50 moles, plus the amount we're adding, which is again 96 grams is what we're adding, and then converting that to moles using the same molar mass of 28. So when we add those both together, we get 7.93 moles. So anytime you're dealing with the ideal gas equation, these parameters, especially number of moles in this case, is going to be the total number that you have, not the amount that you added. So now we have all the numbers we need. So N2, as we said, is 7.93 moles. T2 is the final temperature, which was 273 Kelvin. It cools to that temperature. And then N1 and T1, N1 was 4.50, the amount that we initially started with. And then T1 was 298 Kelvin. And then what we end up with numerically is we want a number with 1 decimal place and no units in kilopascals, so we don't have to do any conversions here. 379.4 kPa. All right, so that's the number that we get there by just rearranging the ideal gas equation and putting in the different parameters that we have before and after. All right, questions on that one? All right, if there's no questions, I'll move on. So number 12. So number 12 is gas stoichiometry. And there's a couple of variations on gas stoichiometry, but in many cases they involve a stoichiometry calculation in combination with the ideal gas equation PV equals nRT to basically relate moles of one substance to its pressure or volume. And then, or there's this one here where actually don't, as we'll see, we don't actually have to use the ideal gas equation. Okay, so this problem here, we have NO and Cl2 react to form NOCl, all of them gases. So the first thing we're going to want to do is produce a balanced chemical equation. And the way that we would want to do this is if we have 2 Cl's over here, we put a coefficient of 2 there. Now we have 2 nitrogens and 2 oxygens, so we put a 2 there. So those are going to be the coefficients for this relatively simple gas phase reaction. 2NO plus Cl2 goes to 2NOCl. And in this problem here, we're looking for, if we have 32.5 liters of NO and 21.2 liters of Cl2 at STP, how many liters of NOCl form? Now there's a couple of things that I can point out about this. So STP, what does that mean? STP is standard temperature and pressure, which means 1 atmosphere is the pressure and 273 Kelvin is the temperature. So if we needed to use ideal gas equation, those would be the numbers. The other thing that's true, but only true at STP, is that if we're at those conditions, 1 mole of any gas has a volume of 22.4 liters. So if we wanted to, we could use the ideal gas equation, or we could use this relationship here, which is true at STP, that 1 mole is 22.4 liters, and we can convert all these amounts into moles and then do stoichiometry like we normally do. However, that's not even necessary here. There's an even faster way to do it, because if we look at the ideal gas equation, PV equals nRT, we notice that volume and number of moles are proportional to each other. They're on opposite sides of the equal sign, so that means they're proportional, which means that in a stoichiometry sense, the volume ratios, the ratios of the volumes of gases that react, is going to be equal to the mole ratios as long as the gases are all at the same temperature and pressure. And so that all that really means for us is that what we can do is we don't have to convert these volumes into moles or anything else. We can just use the volumes directly along with the coefficients as we normally would. So the first thing we have to do is, because we have amounts of both reactants, we need to figure out first what the limiting reactant is. And as I said, normally for a limiting reactant problem, we have to find moles of each reactant first, And we could do that here. There's nothing wrong with doing that. But if we want to save ourselves a little time, what we can do is for each one, to find which one's limiting reactant, we can just take the liters that we have, given that they're at the same temperature and pressure, and divide that by the coefficient. Because, as I said, volume ratios and mole ratios are the same for gas phase reactions. So for NO, we have 32.5 liters, and the coefficient is 2, so that means the stoichiometric ratio is 16.25. And then for Cl2, the stoichiometric ratio is the volume, which is 21.2, divided by the coefficient, which is just 1, and that gives us a stoichiometric ratio also 21.2. So this number is smaller, which tells us that NO is a limiting reactant. All right, and because that's the case, that's where we're going to start our calculation. We're looking for how many liters of NaCl form, and that's going to be, we start with limiting reactant, 32.5 liters of NO, and then we can use the mole ratios as volume ratios, because that's going to be true for a gas phase reaction. So what we find is that 2 liters of NaCl are going to form for every 2 liters of NO that react. They both have coefficients of 2. And so what this means is that if we react 32.5 liters of NO, which is our limiting reactant, we will also form 32.5 liters of the product NaCl. And this would be the answer we would enter in, 32.5. So in problems like this, where all of the reactants and products that we're dealing with are gases, all of them are at the same temperature and pressure, in this case STP, but it doesn't have to be as long as they're all the same. In that case, we can just use mole ratios and volume ratios interchangeably, and we don't necessarily have to convert to moles and then convert back to volume. We can just do it directly. All right, so that's going to be helpful. On some of the problems, you won't be able to do that if you're given masses, or if some of the reactants are liquids or solids, you'll have to use the more typical mole relationships for those. But in problems like this, where everything is in the gas phase, we can save ourselves some time by just doing volumes directly, if that's what the question is asking us for. All right, any questions? All right, I really hope I'm still broadcasting this, because I'm not hearing anything from you guys. So hopefully everything's going smoothly. All right, number 13. We have, in this problem, a 250 milliliter gas bulb filled with 0.379 grams of a gas at STP. Which of these is most likely the gas? Now this problem here has a lot of different ways of doing it. So you may have come up with a different way, and I can talk about those with you offline, but I'm not going to go through multiple ways of solving this, but there's a few different ways of approaching this. Now again, we're at STP once more, so STP is going to be 1 atmosphere and 273 Kelvin. So if we're doing anything with the ideal gas equation, those are going to be the pressures and temperatures we want. This problem here, we can set it up in a few different ways, but basically this is in some sense a density problem. We have the mass of a gas, we have its volume, which is related to density. So what we can do in this problem is we can start with PV equals nRT, as we always do for ideal gases. And because we have the mass given to us, remember that one of the definitions of moles, N, is mass divided by molar mass. Okay, so if we're trying to find which of these gases is most likely, we need to find which one has, we need to find its molar mass and then match it up with the answer. So we're gonna solve for the molar mass of our gas and then match it up to these ones. So for pH3, the molar mass is about 34. For SO2, the molar mass is about 64. For N2, the molar mass is about 28. And for argon, the molar mass is about 40. So these are all significantly different from each other. And so what we're going to do is we're going to solve for molar mass using the information in the problem and match it up with the correct answer choice. All right, so if we look at this problem, then what we're going to essentially do is we're going to take this mass divided by molar mass, and we're going to substitute it in for number of moles N. And so this would give us pressure times volume is equal to mass divided by molar mass times RT, where we're just stating N, number of moles, in a different way. All right? So that's what we have. Pressure times volume is equal to mass divided by molar mass times RT. This is sort of our starting point for the density equation where we solve for mass over volume. In this case, we're just going to be solving for molar mass. And so molar mass is going to be equal to mass times RT divided by pressure times volume. Okay? So in problems where we're dealing with masses of gases as part of it, either in a density calculation or this one here, we can always rewrite the ideal gas equation, solve for our unknown, which is molar mass. And now we just have to put the numbers in. So the mass is 0.379 grams. That's how much of the gas we have. R is a universal gas constant. And then the temperature, because we're at STP, is 273 Kelvin. And then in the denominator, we have pressure times volume. Pressure is 1 atmosphere at STP. The volume does need to be in liters because the universal gas constant is in terms of liters. So we have 250 milliliters, which converts to 0.250 liters. And what we end up with then is 33.98 grams per mole. So all the other units cancel out. Atmospheres cancels. Kelvin cancels, and we're left with grams per mole. Liters also cancels. All right, so we're left with grams per mole, 33.98, which is close to 34. So the best answer choice would be A, pH3. All right, there's again, a few other ways to do this. We could have also remembered that molar mass is grams over moles. So we could have found the moles of gas that we have and just divide the mass by the moles. That would have also been a pretty fast and efficient way to do this. So there's several different setups for this problem that are all conceptually related, and they should all give you the same answer as long as the steps you're following are valid. All right, so any questions on that? All right, if not, I will. All right, good. Someone finally replied because I was worried that you guys were either all out of it or that I wasn't broadcasting properly. So thank you for confirming that you're at least hearing me, because I was getting a little bit worried there. But it's fine. If you don't have any questions, we'll just move on. And this next one here is also gas laws, but here we're dealing with a mixture of gases. So we have a tank containing 3.25 atmospheres of nitrogen and a volume of 9.3 liters, and it's connected to another tank that has 5.33 atmospheres of oxygen with a volume of 15.2 liters. If we open the valve separating the tanks, which allows the gases to mix, what is the final pressure? No reaction is occurring, so we're just mixing the two gases together. Now, in a problem like this where we have a mixture of gases, this is sort of a application of Dalton's law of partial pressures, which states that the total pressure in a mixture of gases is just the sum of the two partial pressures. Pressure of N2 plus pressure of O2. However, we have to be careful in this problem because we can't just add the two pressures together, because initially these two gases are at different volumes, and then we're mixing them together, and so the volume is changing for both gases. So this is going to be true, but only after mixing. We can't just add the two pressures together before mixing. This is only going to be true if the two gases are occupying the same container, the same volume. So what we have to basically do is figure out how the pressure of each gas changes as we allow them to mix together, because initially they have their own separate containers. Once we mix them together, they occupy the full volume, the combined volume of both containers. So for each gas, what we have is from the ideal gas equation, PV equals nRT. Basically, for each gas, the number of moles is constant and the temperature is constant. And so basically this whole thing is just equal to a constant. And we're going to use Boyle's law, P1 V1 equals P2 V2, to find the pressure of each gas after it mixes together, the partial pressure of each gas. So P2 would be P1 V1 over V2. We're going to do that for both gases separately, and then we're going to add them together at the end, because once they mix together, the total pressure is just the sum of the individual pressures. So for N2, the pressure after mixing is going to be P1 V1. So the initial pressure for N2 is 3.25 atmospheres. The initial volume for nitrogen is 9.30 liters. And then the final volume for both gases is going to be the sum of the two volumes, because once we allow the gases to mix together, they're going to occupy the combined volume of both tanks that they were in before. So V2 is 9.30 liters plus 15.2, the two volumes of the tanks that are combining. So the final volume is going to be 24.5 liters that both gases will occupy. So that's what we're going to use for V2 for both of them, 24.5. And so what that means is that after mixing, the partial pressure for nitrogen is 1.23 atmospheres. And then for oxygen, the partial pressure after mixing is the initial pressure for oxygen was 5.33 atmospheres. The initial volume for oxygen is 15.2 liters. And then the final volume, as we said, is the same for both, 24.5 liters. So the final partial pressure for oxygen is 3.31 atmospheres. All right, so those are the two pressures for the individual gases. The total pressure after mixing is going to be the sum of the partial pressures, 1.23 atmospheres for nitrogen plus 3.31 for oxygen. And that's going to be 4.54 atmospheres. And that matches up with choice D down here. Okay, so for mixtures of gases, the total pressure is the sum of the individual pressures, but in this case we had to make sure we got the correct values for the individual pressures, which are the pressures after the gases have been allowed to mix and after the gases are now occupying the full volume. All right, any questions coming in? I don't see any, so let's just keep going. All right, number 15. We're moving towards the end of the chapter 8 material, which deals with what's called the kinetic molecular theory of gases, which is how gases behave at the atomic or molecular level, the speed, the kinetic energy of gas molecules, and so on. And the one real numerical problem that we would have on this topic is what's called Graham's law of effusion or diffusion, which is one relatively simple equation that we have to use. So in this problem, we have 2 atmosphere sample of N2 effuses through a small opening in a time of 2 minutes. If a sample of an unknown gas under the same conditions takes 3.9 minutes to effuse, it should be effused for both, sorry about that. What is the molar mass? So effusion is basically leaking. So if you have a container of a gas and you poke a small hole in it, it's how long does it take for the gas to leak out. And so that's what we're dealing with in this problem. And so whether we're talking about effusion or diffusion, both related to how fast the gas is moving, we have this equation here for the relative rates. So the rate for one of the gases, N2, over the rate of the unknown, which I'll call X, is equal to the inverse square root of the molar masses. So the molar mass of X over the molar mass of N2. And basically this is because we have some questions coming in. Let me make sure there's nothing. All right, yeah, thanks for handling that yourself. So Kimberlin, sorry if I said that wrong, asked about how I got the volume in question 14. That's the sum of the two individual volumes. That is correct. So when you mix together, you're basically you're connecting both tanks together, and that gives you the sum of the volume when they're allowed to mix. So if we're clear on that, I'll move on. Okay, good. Sorry, this got a little bit off sequence here. Okay, back to the problem at hand. So this is the equation for the rate of effusion or diffusion. And basically it's written this way because one of the key concepts from the kinetic molecular theory is that at a given temperature, a heavier gas is going to move slower, a lighter gas is going to move faster. And so basically the rate that they effuse and diffuse is going to be inversely related to the molar mass as a square root. So the faster the rate, the higher the molar mass. The faster the rate, the smaller the molar mass. The smaller the rate, the larger the molar mass. That's the equation for rate. But this question here is dealing with the time that it takes. And so what to think about is that if something is effusing faster, it's going to take a smaller amount of time. If something is effusing slower, it's going to take a larger amount of time. And so what that means is that if we're writing the equation in terms of the time that it takes to effuse or diffuse, N2 over X in the same way, we have to flip the other side of the equation. because something that has a larger molar mass is going to take longer to effuse or diffuse, and so that means the time is going to be directly proportional to the square root of the molar masses. So if we're writing N2 over X, on the other side we're going to have also N2 over X. Okay, so there's two different forms of the equation depending on whether you're dealing with the amount of time or the rate of the effusion and diffusion. So now we can just put the numbers in and solve for this. So the time that it takes nitrogen to effuse is 2 minutes, 2.0. The time that it takes the unknown to effuse is 3.9. Those are both given in the problem. And then the molar mass of nitrogen was not given, but we can figure that out easily. N2 is 28.0 grams per mole. And then the square root of the molar mass of X is going to be down here as an unknown. So basically we'll square both sides of the equation and then cross multiply and divide to solve for the molar mass of X. This algebra is a little bit different than we've seen before, so make sure you're clear on how to do it. And if we do the algebra, which I'm going to skip over for now, the molar mass of our unknown comes out to 106 grams per mole, which matches answer choice B up here. So in problems like this, again, it's really only one equation you have to worry about, although there's sort of two related forms of the equation. And then you're going to use the proper equation and solve for one of the things as an unknown. Sometimes you'll have to solve for just the ratio of the effusion rates or times, and in many cases you'll solve for an unknown molar mass as we did here. All right, so any other questions came in? I think we're updated on the question box, so I'll go ahead and move on to keep things moving, and I'm sure you guys all have different places to be, maybe not better places to be, but definitely different places to be, so let's try to keep moving. On to number 16. We're going to know which of the following statements about ideal gases is false. So this is kind of a combination of ideal gas concepts as well as kinetic molecular theory, which relates to kinetic energy and temperature. Okay, so for choice A here, we're looking for the false statement in this case. In a mixture of two gases, A and B, the total pressure depends only on the total moles of A and B, not their identity. And this one is sort of related to the problem we did a couple, I think number 14, where we had a mixture of gases. And even though we didn't do it in terms of number of moles, the ideal gas equation, PV equals nRT, only depends on the number of moles of the gas. It doesn't depend on what it is. So whether you have one individual gas or a mixture of a bunch of gases, if you know the total number of moles you have, you can solve for pressure, volume, and temperature. And so this one is going to be true. We're looking for the false statement, so it's not going to be the answer choice, but this one is true because anytime you have a mixture of gases, all you need to know to find the total pressure is the total number of moles, not the individual moles of each, and not what the gases are is not going to matter. PV equals nRT only depends on N, has nothing to do with what gases you have. All right, so that one's going to be true. If we go to choice B here, this is where we're getting into more kinetic molecular theory, kinetic energy and velocity. Samples of helium and O2 at STP have the same average kinetic energy. So the key concept for kinetic molecular theory is that the average kinetic energy of a gas only depends on the temperature. Okay, so that's the only variable that influences kinetic energy. And so if you have, and what that means is that if you have two gases at the same temperature, they're going to have the same average kinetic energy. It doesn't matter what the two gases are. And in this case, they're both at STP. So if you're at STP, that means both gases are at 273 Kelvin, and that means they will have the same average kinetic energy. So for kinetic energy, all that matters is going to be the temperature. If the temperature is the same for two gases, their kinetic energy on average is the same. All right, so this one would also be true. If we go to choice C, this is related, but now deals with molecular speeds. So in this case, we have, again, two gases at the same temperature, helium and oxygen, and they have different average molecular speeds. O2 is higher, so let's evaluate this one. So at a given temperature, kinetic energy, as we said, is proportional to the temperature, and the definition of kinetic energy is 1/2 mv squared. Where the bar just means average, of course. And what this means, we can also rewrite this in terms of molar mass, as we often do for the the previous problem that we just did. But what it means is that if you have the same kinetic energy, which would be true if the temperature is the same, the one that has the larger mass is going to have the smaller velocity. It's going to be moving slower. Okay, so O2 is much heavier than helium. O2 has a molar mass of 32. Helium has a molar mass of 4. So at the same temperature, where they have the same kinetic energy, you would expect O2 to be moving slower on average. Here it says that O2 has a higher average velocity, so this one would be false. Okay, so when you're comparing two gases at the same temperature, the one that has the higher molar mass has the slower average velocity, and vice versa. The one that has the lower molar mass would have the faster average velocity. All right, and then finally for choice D here, deviations from the ideal gas law are smallest at high pressure and low temperature. And so when you're thinking about deviations from the ideal gas law, this is dealing with what we call real gases. So no gas is going to perfectly behave as an ideal gas. And when you have deviations from PV equals nRT, the ideal gas equation, those are going to depend on what gas you have and what conditions the gas is at. So if you're looking for the smallest deviations from the ideal gas behavior, basically if you want the gas to follow the ideal gas equation as closely as possible, what you want is you want the gas molecules to be as far apart as possible so that they're not interacting with each other too much and so that they take up very little volume on their own. And you want them to be moving as fast as possible so that they behave more like a gas and so they don't communicate or interact with each other for as long of time. So if you're looking for the smallest deviations, what you want is you want low pressure or large volume. Basically, you want the gas molecules to be spread apart as far as possible. You want the temperature to be high so that they're moving as fast as possible and not interacting with each other. And as is sort of relevant to the concepts in Chapter 9, you want to have the smallest intermolecular forces possible so that the gas molecules don't attract to each other. Because the ideal gas equation assumes that the gas atoms or gas molecules are not interacting with each other at all, that they're just bouncing off each other and not sticking together at all. So if you have small intermolecular forces, that's going to largely be true. And similarly, if you spread the molecules far apart and you have them at a high temperature so they're moving really fast, that's going to allow them to behave more like a gas. So if you want the smallest deviations, what we're looking for, in this answer choices, it says deviations are smallest at high pressure and low temperature. That's the opposite of what should be true. So this one is also false. If you go to high pressure and low temperature, you're going to force the gas molecules close together and you're going to force them to be moving slower such that they're going to interact with each other more strongly, and that's going to cause deviations from the ideal gas law. So both C and D are going to be false in this problem. Okay, so that's a conceptual question. There's several related concepts sort of towards the end of Chapter 8 that deal with kinetic molecular theory, real gas behavior, and a lot of things that are covered in this very problem here. We don't expect you to have a real in-depth knowledge of those, but there will likely be one question on your exam that is going to deal with some of these more conceptual aspects that came up at the end of Chapter 8. Okay, so any new questions come in? I don't see any. I have notifications allowed now, so I won't miss any of your questions if they do come in. We did have one, so let's see what it says. So only volume affects number of collisions. Temp only makes molecules move faster. So we're talking about the number of collisions, which is related to this problem but not directly involved in any of these answer choices. So the number of collisions is going to be affected by both volume and temperature. So if the volume increases at constant temperature, basically if you make the gas molecules spread apart more, you're going to have less collisions per unit time. And that's because the gas molecules are spread further apart, so they don't collide with each other as much and they don't collide with the wall of the containers as much because they're moving through a larger space. If you increase the temperature, you're going to have more collisions on average, all else being equal. Because if you increase the temperature, the gas molecules are moving faster. If they're moving faster, they're going to run into each other more often, and they're going to run into the walls of the container more often. So for a lot of these concepts dealing with kinetic molecular theory, it is important to think about how many collisions the gas molecules have with the walls of the container and with each other on average. Also how strong these collisions are. So the strength of the collision is going to be influenced only by the temperature. So if you increase the temperature and all else is the same, you'll have also stronger collisions. And so when you raise the temperature, both of these will contribute to raising the pressure of the gas, because they're going to collide with the wall more frequently and they're going to collide with the wall with more force. And so really both of those affect the number of collisions, and the temperature will also affect how strong the collisions are. So that is an important related concept. And then it says, but you said when the temp increases, they have no attraction to each other. So sort of the number of collisions and the attraction is two separate things. So in an ideal gas, the gas molecules are colliding with each other all the time, but the ideal gas equation assumes that the collisions are elastic, meaning that the gas molecules just bounce off of each other and don't stick together. In real life, if you have intermolecular forces, the gases are going to attract to each other to some extent. And the slower they're moving, they're going to attract to each other. They're going to start behaving more like a liquid, because when you slow them down, they're going to spend more time near each other. And if they spend more time near each other, that attraction is going to become more significant. So they will collide more frequently at higher temperature, but in the situation where they're moving fast and where the intermolecular forces are small, those collisions would be elastic, and that wouldn't cause any deviations from the ideal gas law. All right, so if we're clear on that, then I will go ahead and move on. And we're getting in now to the Chapter 9 stuff. So as you'll see on this practice exam, the Chapter 9 material is only about 4 questions on the whole exam. We're covering the first 6 sections, and I know it's not ideal that the lecture material was scrunched up so close to the exam. I apologize for that, but that's mostly because we lost a week earlier in the semester. But we don't have in Chapter 9, there's several different topics, I suppose, but we don't ask you to really know any of them in any great level of depth, and we got rid of some of them towards the end that's going to make your final exam preparation a little bit easier anyway. But for this exam, we cover the first 6 sections of Chapter 9, and the first major topic is intermolecular forces, which we sort of alluded to in the last problem. So in this problem, we're just asking the simple question, which intermolecular forces are present in a sample of SF4? All right, so the first thing to consider is, we have basically 3 different types of intermolecular forces. So we have London dispersion, we have dipole-dipole forces, and we have hydrogen bonds. These are the 3 types of intermolecular forces, and if we ask you about the relative strength of them or how that influences the properties, remember that they increase in strength in this order. London dispersion is the weakest, then dipole-dipole, then hydrogen bonds. This one is just asking which of these forces are present in this molecule here, SF4. So we can keep in mind, like, what are the characteristics that are required to have these different types of forces. So London dispersion forces occur in everything, at least everything that has electrons, which is every chemical substance in the world. So anything that has electrons is going to have London dispersion forces. Even the simplest, tiniest atoms and molecules you can think of will have at least some London dispersion forces. So this is going to be present in SF4 because it's present in everything. Dipole-dipole forces are only present in polar molecules. Anything that's polar will have dipole-dipole forces. Hydrogen bonds is a special type of dipole-dipole forces that occurs in molecules that have OH, NH, or FH bonds. So those bonds are not the hydrogen bonds, but it's a type of intermolecular force that exists when you have OH, NH, or FH bonds, which are very polar bonds, and then also because hydrogen is so small, it allows those molecules to pack very closely together and thus have particularly strong interactions. So in this molecule here, we clearly don't have hydrogen bonds because we don't have any hydrogen in the formula, so we can't have hydrogen bonded to oxygen, nitrogen, or fluorine. So this one's out, and that's not even one of the answer choices anyway. We also see that choice B, covalent bonds, this is not an intermolecular force. SF4 does have covalent bonds, but that is an intramolecular force. Remember that intra means within, and inter means between. Here we're dealing with the intermolecular forces, which are forces between 2 or more different molecules of the same type. And so the last one we have to really evaluate is, do we have dipole-dipole forces? And for that, we have to know if the molecule is polar. So as a review of figuring out if a molecule is polar or not, in SF4 we have to figure out first the Lewis structure and then decide the molecular shape and then decide if it's polar. So this is reviewing back to chapter 4. So in some of these questions we are going to have to know whether the molecule is polar or not to evaluate whether or not it has dipole-dipole forces. So if we go to the periodic table, we see that sulfur has 6 valence electrons, it's in group 6, and then fluorine is in group 7, so each one's going to have 7 valence electrons. So when we count electrons for this molecule, we're going to get sulfur has 6 valence electrons, there's only 1 sulfur in the formula. And then for fluorine, we have 4 fluorines and each contribute 7 electrons, so that's going to be 28. And so we have a total of 34 valence electrons in this molecule. When we draw the Lewis structure, what we end up with is 4 single bonds to fluorine. We complete the octet of fluorine first, so we're adding 6 more electrons or 3 lone pairs to each fluorine. 4 complete octets is a total of 32 electrons. We have 34 in total, so that means 2 more go in the central atom. So this ends up as AX4E in the AXE notation, and we don't need to even go so far as to figure out what the shape is and all that stuff, because as we talked about a lot in the context of the last exam from the chapter 4 material, anything with 1 lone pair is polar. Okay, so SF4 is in fact polar. It has 1 lone pair, and that's true of anything with 1 lone pair. And so because it's polar, it will have dipole-dipole forces, and that means the correct answer for this problem is 2 of these. This molecule will have London dispersion forces and dipole-dipole forces. It will also have covalent bonds, but that is not an intermolecular force, that is an intramolecular force. All right, so that's sort of the first major topic in chapter 9 that we'll cover on this exam, which is identifying the intermolecular forces. If we go to question 18, this is also related to intermolecular forces, and it's sort of asking how does intermolecular forces affect the properties of a substance, in particular phase change properties. So we want to know which of the following does not increase with the strength of the intermolecular forces. And so thinking about this one conceptually, basically, if the intermolecular forces are stronger, that means the molecules are held together more tightly. And if they're held together more tightly, that means you have to put more energy in to separate them, which means the phase changes all occur at higher temperatures. So if they're in the solid phase, if they have stronger intermolecular forces, you have to heat them to a higher temperature to break up the molecules and allow them to become a liquid. And similarly, if you have a liquid phase and you have stronger intermolecular forces, it's going to require a higher temperature to break up those molecules and send them into the gas phase, and thus the boiling point is also higher. So both the melting point and the boiling point increase when you have stronger intermolecular forces, so that's not going to be our answer. The other 2 are properties of liquid, viscosity and surface tension. So it is helpful to know the definitions of these briefly. We're not going to, again, ask you a lot of details about these, but viscosity is the resistance to flow or the thickness of the liquid, is a more colloquial way of thinking about it. So viscosity, if you're comparing, gasoline to motor oil, gasoline has relatively low viscosity, and then motor oil has higher viscosity. It's a thicker liquid, it flows more slowly. So that's what viscosity is. And then surface tension is a little bit hard to define, but it's the resistance to increase the surface area of a liquid. And so what that essentially means is that at the surface of the liquid you have sort of almost a rigid surface, not perfectly rigid, but a little bit of rigidity at the surface because the liquid doesn't want to spread out any further than it already is, and that's resistance to increased surface area. Surface area is basically the reason why you can float a paper clip on top of water. Surface tension is why you can, at least briefly, if you're careful, float a paper clip on top of water, because the surface tension of the water holds the paper clip up, even though in the bulk the density of the water is less than the density of the paper clip. All right, so those are 2 quick definitions of those, but the key part of this problem is that both of these will increase with increasing intermolecular forces. So if you have stronger intermolecular forces, both the viscosity and the surface tension will increase. So these are 2 other properties that will increase. So the last one, which should be our answer, because we're looking for the one that does not increase ideal gas behavior, this one we also talked about in the previous problem. So if you have strong intermolecular forces, the gas molecules are going to start attracting to each other. The ideal gas equation, the ideal gas law, assumes that they're not attracted to each other, and so stronger intermolecular forces is going to lead to deviations in the ideal gas behavior. And so this would be the correct answer here, because ideal gas behavior would be assuming that you don't have any intermolecular forces. So if you increase the intermolecular forces, the substance is going to behave less like an ideal gas. Okay, so that is that one. Any questions? All right, moving on to the last two. So one of the major topics in chapter 9 was the structure of metallic solids. So we're talking about now solid state crystalline materials where the atoms are arranged in very regular repeating patterns, and we're dealing with primarily cubic structures. And one of the big things we're going to ask you to do, we're not going to really ask you to obviously memorize the structures of all these different metals, but we want you to be able to sort of understand how the atoms are arranged, and especially how to count them when they're arranged in a cubic unit cell. So that's what this question is asking us to do. So we have a partially filled cubic unit cell with 4 corner atoms, 2 face atoms, and 4 edge atoms. How many total atoms are there in this partially filled unit cell? All right, so in a cubic unit cell, remember the unit cell is basically the smallest repeating unit of a crystal structure. The rest of the crystal is just generated by stacking these cubic blocks on top of each other in all directions. So you'd have one of these cubic cells, defined as a cube as the name implies, and I'm okay at drawing cubes, not the worst. And in a cubic unit cell, there's basically 4 different places that we can put atoms. So one would be to put them in the face of the unit cell. That's right in the middle of one of the square faces. So in blue, I'm showing here the face of a unit cell. That's where we put an atom right in the middle of one of the squares. We also have corner positions. That would be where we put an atom right in the corner of the unit cell, as the name implies. And then we have edge positions as well. These don't show up in metallic crystal structures typically, but they would show up in ionic compounds, which we're going to skip, but we should still at least know a little bit about the edge positions and just how to count them, even though we're not going to deal with them too directly. So those are 3 positions, and then the last position is right in the middle of the cube. So it's going to be a little bit hard to draw if you have to imagine this in 3 dimensions, but if you put an atom right in the center of the entire cube, that's what's called the body center position. So these are the 4 different places we can put atoms, and basically all these different positions are shared in different ways by the neighboring unit cells. So a face of a cubic unit cell is going to be shared by 2 unit cells, which means if we're counting the atom for that individual cell, it counts as 1/2. Because it's shared between 2 unit cells, so it counts as just 1/2 of an atom for that cell. The corner positions are going to be, I'll put these in the same colors so we can keep them color coded. The corner positions are going to be shared by 8 unit cells, and so that means they count as 1/8. Edge positions are going to be shared by 4. So they're going to count as 1/4 each. And then finally, the body center position, which we don't actually have in this problem, but just for completeness, I'll include it. This is not going to be shared because it's completely inside the unit cell. So it's, when you stack the blocks together, it doesn't boundary 2 different or more than 2 different cells. It's just right in the middle of one of them. And so that's going to count as a full atom. All right, so those are the different ways that we count the atoms when they're arranged on a cubic unit cell. And so for this problem, that's all we're doing, is we're just going to count them in this way. So the number of atoms is going to be, we have 4 corner atoms, and each of those, as we said down here, counts as 1/8. We have 2 atoms on the faces, and those each count as 1/2. Then we have 4 atoms on the edges, and those each count as 1/4. They're shared by 4 unit cells. And so what we end up with is 2.5 atoms, which of course it sounds weird to talk about a half of an atom, but basically what it means is that some of the atoms are shared between 2 unit cells, so the ones that actually belong to this individual cell would be 2.5 of those atoms that are present on the unit cell boundaries. All right, so that's one thing we'll ask you to do is count the positions. That was very recent material, so if you're even if you're caught up on lectures, you might have just seen that or not seen that quite yet, but there is time to review that, and that's not too much we need. So the question is, how do we know the corner position has 8 atoms? The question that just came in. So this is, to be clear on this, it's not that the corner position has 8 atoms, it's that the corner positions are shared by 8 unit cells, which means they count as 1/8. Now that said, there are 8 corners, so if you filled every single corner, you would have 8 of them present in the corners. But then each one of those atoms is going to be shared by 8 different unit cells and are count as 1/8. Now to understand why that is, because I'm a terrible artist, I'm not going to be able to draw this in 3 dimensions, but there are pictures in the notes that hopefully will make this clear. But what you can think about is if we stack these unit cells together in all directions, if we're looking at the faces of the unit cell when they stack together, they're going to be like this. So these are 4 different unit cells looking at their faces. So a corner atom would be right there. So it's going to be shared by the 4 cubes that are below the plane of the face that I'm showing and by the 4 unit cells that are above the plane that I'm showing. So each corner position is shared by a total of 8 cubes. So when you stack cubes together, if you have blocks at home, or more likely if you have younger siblings or whatever, or kids of your own that have their own cubic blocks at home, you can play with them. It's sort of a good visualization for this. If you stack cubic blocks together in all directions, each corner is going to be shared. It's going to be shared by 8 different blocks or 8 different cubic unit cells in the context of chemistry. So this is a corner position where you have 4 sort of next to each other, 4 faces, where you're going to have 4 cubes below, 4 cubes above this. All 8 of those are going to be sharing this one atom that's at the corner. So that's where we get the 1/8 from for corner atoms. There is a table in the notes that I believe there is anyway, that sort of summarizes all this. So I encourage you to look at that. As I said, it's the more recent material. So if you haven't gotten to it yet, there's still some time before the exam. I again apologize for the lectures and the exam being so close to each other. But that's sort of one of the main things we want you to know is how to count these different positions in a cubic unit cell. There's going to be potentially questions that come up like that on the exam. All right, so on to the finale, number 20 here. The last thing we're going to talk about in this is sort of classifying substances and sort of understanding how the properties relate to the type of substance that it is. So here we have an element is found to be a good conductor of electricity, high boiling point, and malleable. Which of the following could be that element? So what this problem is really asking us to do is distinguish between metals and nonmetals. Okay, so there's sort of, this is sort of the grossest division of the periodic table, metals versus nonmetals. There's other classifications that we talked about in this chapter, especially classifying the different types of solids that we have, metallic, ionic, and so on. But if we're talking about just elements, really at the most basic level, it's either metal or nonmetal, and that's going to have a big effect on the properties that they have in most cases. Okay, so if we look at sort of the important properties and how they're different between metals and nonmetals, if we're talking about either electrical or thermal properties, metals are good conductors. So they conduct electricity. They also conduct heat very well because they have very loosely held outer electrons, whereas most nonmetals are insulators. All right, the exception to this would be graphite, which is the form of carbon that has very delocalized pi electrons. That's a conductor, but just about every nonmetal is an insulator. And then metals, in terms of their what we call the mechanical properties, they're malleable. That means that we can bend them, we can shape them. They don't fracture or crumble very easily. But most nonmetals are brittle, meaning that if you try to change their shape, they're just going to crumble. They're not going to be able to mold them and shape them very easily. In terms of their phase change properties, which is sort of the other key thing of this problem, metals tend to have moderate to high melting points and they tend to have very high boiling points. Okay, so MP melting point, BP boiling point. So metals are moderate to high melting points and high boiling points. And then nonmetals are going to have, both of those are going to be comparatively low. Low melting points, low boiling points, because they have, in general, relatively weak intermolecular interactions, much weaker than the metallic bonds that you would have in a sample of metal. Okay, so those are kind of the key properties that distinguish metals from nonmetals. This is what we're doing here. So if the substance we're dealing with here is a good conductor of electricity, has a high boiling point, and is malleable, that means we're looking for clearly a metal. And so we just have to look at the 5 answer choices and classify them either as a metal or a nonmetal. And as a reminder of how we do that, that comes from the periodic table. Substances on the right are nonmetals, substances on the left are metals. And the dividing line again sort of occurs here, starting between boron and silicon and sort of snaking its way down as a staircase. So that's sort of the dividing line between metals and nonmetals. So we have in this problem sulfur, clearly a nonmetal, phosphorus, clearly a nonmetal, neon, clearly a nonmetal, but then gold is over here. It's a transition metal, so that's the one metallic element, and then iodine over here is also a nonmetal I. Should have given you the symbol for some of these because they're beyond atomic number 36, but gold is AU. That should have been in the problem. I apologize for that. Iodine is I. The rest of those we should know. But anyway, the only one that's a metal is over here, gold, AU, which is a transition metal. And so because that's a metal, that's going to be the one that we would expect to have these basic properties, and that's the answer that we want to pick. Okay, so that's how we would approach this problem here, just classifying substances as metals or nonmetals. We also should keep in mind that the in-between elements, which we didn't ask you about here, the ones that are sort of close to the staircase, like especially silicon, boron, silicon, germanium, antimony, these few elements here, those are what we would call the metalloids, arsenic as well. And those ones have properties that are sort of in between metal and non-metal. And those are what we would typically call semiconductors, which means they conduct electricity well at high temperature, but not at low temperature. And so there could be some questions about semiconductors on the exam as well. So review that part of the notes, but as long as you know it at the level of detail that's in the lecture notes, that should be more than sufficient for the exam. We're not going to go into great detail on any of these topics. All right, so I think that takes us to the end of what I wanted to cover. If there's any last questions, shout them out or send them in right now. And then if not, I will wrap this up very soon here because I know we've been at this for a while and I think you were sticking around. The last question that came in is the phase change graph stuff going to be on the test? So I think you're talking about phase diagrams. That will only be on the final exam. So there's 2 sections of Chapter 9 that deal with phase changes. One, which is I think I don't remember the numbers, I think it's section 9.9 or so, deals with phase change enthalpies and things like that. That topic has been omitted, and that's clearly outlined in Blackboard with the lecture notes. The very last section of Chapter 9 is phase diagrams, and that doesn't involve really any math. It's just knowing how to read those diagrams. That will be covered, but only on the final exam, not on this exam. Okay, so if there's any other questions? All right, going once, going twice, and if not,
Thank you.
Yep, you're welcome, everyone. Thank you for coming. It was great to have you all here, and I know it's a busy time of year for you, so I especially appreciate you taking the time to come. I will put this recording onto YouTube later today if you want to revisit anything, and then I'll post the solutions as well. So we'll have 2 more of these next week for the final exam. We'll split the final exam into 2 pieces. Hopefully each one won't be as long as this because it's going to be just 17 problems each instead of 20. And I hope to see as many of you there as possible. And if you have any other questions related to this exam or the final, I'll be around. I've got, as most of you can imagine, not much to do these days. So please be in touch if you have any questions. All right, take care, everyone, and I'll see you next time.